Hello, everyone. Thanks for joining us online today. Having a bit of issues with our cameras, but hopefully everyone can hear me with my microphone. First, I'd like to just hope everyone's doing well. Wish you and your families well. Hope you're staying safe and staying healthy during these challenging times. So today our webinar here is presented by Stephanie Munten. She is a researcher at Laurentian University, and she works predominantly at the LEAP lab. So that's the Laboratory for Environmental and Exercise Physiology. Today, her topic will be on changes to the environment and its effect on the human body and work performance. Her presentation is approximately 30 minutes. At the end, we'll have a question period. So if anyone has any questions, please enter those into the chat box, and then we'll go through all of them at the end with Stephanie. So for now, Steph, I will mute myself, and I'll turn the spotlight over to you and let you begin whenever you're ready. Thanks.
All right. Thanks, Brandon. I'm excited to be here today and talk to you about multi-stressor environments and how they affect human performance. So the effects of environmental temperature and oxygen availability on human physiology have been studied widely, but almost entirely independently. So on Earth, environmental stressors aren't always present in isolation. So changes in altitude are usually associated with a change in ambient temperature. So even though the effects of each of these stressors has been well documented individually, the research that has examined combined effects of temperature and altitude to date has been limited, and varying results have occurred. So ascent to altitude is typically associated with a decline in ambient temperature, but there are some locations throughout the world where ascent to altitude is combined with warmer temperatures. And what makes the combination of increased environmental temperature and altitude interesting is that they both have a large effect on the cardiovascular system, right? They limit blood flow and oxygen delivery throughout the body. So ultimately, research in this area can be beneficial for individuals who work in these extreme environments, and occupations that come to mind for me are military personnel, firefighters, search and rescue, anyone where their environmental location might change very rapidly, and they may be required to perform their duties immediately without any acclimation period. So I'm going to quickly talk about each environmental stress individually and cover some physiology, and then we will get into the research that has looked at these combined environments. So when we talk about a hot environment, we usually describe it in terms of the air temperature, right? It's 35 degrees Celsius outside. But there are some other factors to consider when we're quantifying heat stress, right? Is the heat stress dry or humid? So just like when we take into account wind chill, when we talk about cold temperature, we need to consider the level of humidity when we talk about a hot temperature. The more humid it is, the harder it is for the exchange of heat between the body and the environment. So we typically exchange heat to the environment predominantly through evaporation of sweat, but when it's really humid, it makes it really hard for that transfer to occur, and ultimately it can make the environment feel hotter. Another factor to consider is the heat that's produced by the body, or our metabolic heat production. So coupled with the environmental load, the body generates its own heat, particularly when the body's in motion. So the intensity of the work or exercise that's being completed can factor in how hot that environment feels. So moderate increases in body temperature are actually beneficial to performance. They enhance the speed of chemical reactions such as nerve conduction, cellular metabolism, muscle conformation changes. But if body temperatures are elevated excessively, the body reaches a state of hypothermia and performance can be impaired. And this is primarily influenced by the central nervous system and the cardiovascular system, which promote peripheral fatigue. Now, when an individual ascends to altitude, the pressure of the air decreases, the barometric pressure drops, resulting in a drop in the partial pressure of oxygen. And this decreases the amount of oxygen that's available to the individual. So hypoxia refers to these low oxygen conditions. Now, the physiological response to altitude or hypoxia is dependent upon the level of oxygen availability. So how high of altitude are you simulating or are you at? The exercise intensity or the work intensity that's being done, and the level of acclimation. Is this acute exposure or long-term exposure? Now, for this webinar, we're going to focus on the acute exposure to altitude. And based on these factors, there's going to be physiological adaptations that need to occur in order to maintain adequate oxygen supply throughout the body. So in terms of altitude, I kind of just wanted to make it really clear when I start to talk about different ranges. So when I refer to moderate altitude, what are we really talking about? And I thought this figure put it into perspective fairly well. So if we look at the first row here, we see that altitude increases in different areas of the world. So we are most used to sea level. So in this example, they use Miami, Florida as their location, but Sudbury itself is also very close to sea level. We're only about 350 meters above sea level. And then above that, we kind of get into moderate altitudes. So anything from 1,500 meters to 2,500 meters is considered moderate altitude. And then above that, you have high altitude, which extends up to 4,500 meters. You also have two ranges above that with extreme altitude being considered what Mount Everest would be. So as you can see, as altitude increases, the barometric pressure starts to decrease. But what's interesting is that the actual percentage of oxygen in the air stays the same, right? It's always 20.9%. But because the barometric pressure drops, you see that drop in the partial pressure of oxygen. Now, in the literature, we often refer to the degree of altitude as a percentage, or more specifically, the fraction of inspired oxygen. So with each breath, how much of that air is oxygen? So in the moderate range, your fraction of inspired oxygen can range from 17.3% at the low end to 15.5% at 2,500 meters, roughly. And then at high altitude, your fraction of inspired oxygen can be as low as 12.3%. So the majority of the literature we're going to talk about today is in the moderate range, but there are a few studies that kind of dip into that, the low, high-end altitude. So briefly talk about some physiology, and I know it's not an area that a lot of people are familiar with, but I think it's important to express how both of these environments influence our physiological systems. So during dynamic exercise in a hot environment, we have an increased requirement for blood flow to active muscles in order to generate energy. But at the same time, there's increased thermoregulatory requirements for blood flow to the skin in order to regulate body temperature, right? To exchange heat from the body to the environment. The increased demand for blood flow results in an increase in cardiac output to compensate. And this is primarily completed through an increase in heart rate. And this is especially important when ambient temperatures are really high, because stroke volume can be lowered due to a combination of impaired venous return and shortened diastolic filling time. So during longer duration exercise in the heat, fluid loss through sweating increases and dehydration can occur. When significant dehydration develops, there are reductions in plasma volume and blood pressure, ultimately affecting the cardiovascular response. But the decline in plasma volume could also threaten oxygen delivery to the muscles. and impair aerobic energy turnover. So we must rely on a greater extent on our anaerobic systems, and this provokes lactate and hydrogen ion accumulation, eventually reducing total ATP regeneration and causing fatigue. So in a hypoxic environment, you have a disruption in the diffusion of oxygen to in the lungs to the blood. And this causes arterial oxygen content to decrease. Ventilation then increases as chemoreceptors sense that change in the partial pressure of oxygen, increasing the respiration rate and producing a response similar to hyperventilation. And this is known as the hypoxic ventilatory response. The goal of this response is to improve blood oxygenation, but it also reduces arterial oxygen, carbon dioxide content, as a large amount of CO2 is expelled from the lungs. This can cause a small rise in blood pH, also known as respiratory alkalosis. Additionally, you also have a leftward shift of the oxygen dissociation curve to hemoglobin. And this is to increase loading of oxygen at the lungs to hemoglobin in the blood. That increased affinity does put more oxygen in the blood, but it will also limit the amount of oxygen that is released and unloaded at the tissue level in tissues such as muscle. So this can accelerate the rate of peripheral fatigue as it directly affects muscular metabolism. Additionally, upon exposure to hypoxia, you have an initial increase in cardiac output, primarily done through an increase in heart rate in order to ensure adequate oxygen delivery throughout the body. And with longer exposure, either loss of plasma volume is common, increasing the stress on the cardiovascular system, and also limiting high intensity or prolonged exercise. So as you can see, there's a really large influence on our cardiovascular system in both environments. So it's kind of really interesting to see how, putting these two environments together, how are we going to respond? So just before we get into the actual literature, I just really want to define two terms that I'm going to be using a lot to define the relationship between our conditions, so our increased temperature and altitude. So the first term is a no interaction. And when there's no interaction, it means that the decline in performance due to stressor A, in this case, we'll say it's heat, plus the decline in performance due to stressor B, in this case, let's say it's altitude, is equal to the decline in performance in stressor C or the combined condition. Another way to look at this is that there is an additive effect. 2 + 2 = 4. Now the second term is an interaction. And this is when the combination of stressor A and stressor B is not equal to the decline in performance during the stressor C or the combined condition. So in this case, 2 + 2 = 3. Also the reverse can happen, 2 + 2 = 5. So I'm going to be referring to these terms a lot, and I really hope you don't get confused because it can get a little jumbled. So the very first research study that looked at the combined effects of these stressors was completed by Girard and Racinet in 2014, and they looked at combined stressors during time to exhaustion cycling trials. So if we orient ourselves here, we have time to exhaustion on our y-axis and our conditions on our x-axis. And what they found was that performance was reduced by approximately 1/3 in their hot condition at 35 degrees Celsius. It was also reduced by approximately 1/3 in their hypoxic condition at 15% fraction of inspired oxygen compared to our control trial. And that when the conditions were combined, they saw that performance was reduced by a little bit more than half. So they observed an interaction between these two variables. Specifically, the decrease in physical performance was greater, but less than the predicted sum of performance decrements when heat and hypoxia were measured independently. Now, Lloyd and colleagues in 2016 also saw the same performance outcome when they combined 40 degrees Celsius heat stress with 12.5% FiO2 during isolated limb exercise to exhaustion. So again, they saw that when the conditions were combined, which is kind of in this middle bar right here, the combined effect was significantly less than the sum of the individual effects. And this is kind of interesting because originally when I started looking into this topic, I would have thought, well, when you put the two stressors together, you should see that additive effect. But in fact, there are studies that are showing, well, no, performance doesn't actually decrease as much as we would anticipate. So, however, there are some studies that do not see that interaction. Instead, they see that additive effect. So Van Kustum and colleagues in 2015 saw no interaction between mild heat stress at 25 degrees Celsius with moderate hypoxia. So during a 30-minute cycling time trial, where they asked participants to complete as much work as possible in 30 minutes, they saw that the temperature, so the heat stress, brought about a small but significant decrease in performance of 3.2%. And in the altitude condition, they saw a significant reduction at 34.3% compared to the control trial. And that when the conditions were combined, they saw an additive effect where performance was reduced by 38%. And one last study, Aldis and al. In 2016 also saw this additive effect when athletes completed a soccer fitness test while exposed to heat and altitude. So if I kind of summarize these studies here, you can kind of see there's two different things happening. We have two studies that saw an interaction and two studies that didn't. They saw that additive effect. And while the range of altitude seems to be fairly wide, there seems to be a pretty specific divide between high ambient temperatures and lower or milder ambient temperatures. So this kind of drove this, well, maybe it's the magnitude of the environmental stress that's driving this interaction. But one more thing I want to point out is that the two studies that saw the interaction used time to exhaustion protocols, while the two studies that saw no interaction used a time trial-based protocol. So based on these four studies, it kind of drove the research question from my own research thesis, where we speculated that if you have someone perform a task at lower ambient temperatures at 25 degrees Celsius, like the Van Kustum paper, we should see no interaction. And then if they perform it again at a higher ambient temperature, say 35 degrees Celsius, like Jordan-Racinet, that relationship should shift if this theory is correct. So that's what we did. We had participants complete 20-kilometer cycling time trials in 6 different environmental conditions. So we had 3 temperatures. We had cool at 15 degrees Celsius, warm at 25 degrees Celsius, and hot at 35 degrees Celsius. And each of these temperatures were completed at sea level or normoxia. So that's bottom line here, and as well as altitude in our hypoxic condition at 15% FiO2. So what we saw was that time to complete that 20-kilometer time trial increased independently in our temperature conditions. So the hot conditions were always longer than the cool conditions, regardless of the level of altitude, if it was done at sea level or at moderate altitude. And all of the hypoxic conditions took longer than the sea level conditions. So we did not see an interaction. The increase in time to complete that time trial was proportional when the stressors were combined. And as you can see, these are two very, very straight lines that are not intersecting with each other. So we didn't see what we were expecting. Now, the very last, most recent study that's investigated the effects of heat and hypoxia was completed by Bradbury and colleagues in 2019. And they had individuals complete a 15-minute self-paced time trial. So they did as much work as they can in 15 minutes. And again, they had 4 environmental conditions. Their sea level thermoneutral, sea level hot at 35 degrees Celsius, their hypoxic condition at 14% FiO2, and then the combined hot hypoxic. And surprisingly, they found that exercise performance in the combined heat and hypoxia trial was not equal to the sum of decrease in performance in each of the environmental stressors alone. So again, they saw that interaction. So there still seems to be a lot of varying results between each of these studies. And we'll kind of maybe get into 2 reasons why these things might be happening. But first, I want to quickly talk about the physiological response. So we talked a lot about the performance outcomes, but what's happening to our physiological systems? Surprisingly, all of the physiological responses have been fairly consistent between research studies. So when exercise was performed during heat stress, body temperature always rose. When exercise was performed at altitude, all studies saw a decrease in the saturation, arterial saturation of oxygen. And in all cases, heart rate increased proportionally and was the same at the end of exercise in all conditions. So none of these physiological variables are significantly different or exacerbated during the combined condition compared to each environment on their own. So body temperature rose to the same degree, regardless of if exercise was performed at sea level or at altitude. Any condition that involved altitude saw the same decrease in the saturation of oxygen, regardless of the environmental temperature. So no clear physiological mechanism or variable has been identified as being different from either the heat or hypoxic stress alone compared to the combined condition. And these results were further confirmed by 2 studies, Coombs and Charcudian, who found that exposure to hypoxic conditions had negligible effects on the thermoregulatory function or core temperature response to exercise in warmer ambient temperatures. So if we're seeing the same physiological response in all of these studies, but we're getting different performance outcomes, why might that be? So there's 2 proposed mechanisms at the time. The first is proposed by Lloyd and colleagues in that 2016 paper. And they proposed that we respond to multi-stressor environments based on a worst strain takes precedence principle. And based on this, this proposes that the interaction might be regulated by the impact magnitude of each stressor. So when a large stressor, or when a stressor has a large influence, it can antagonize or interact with the other stressor when they are combined. So this is what we've seen with the hypoxia and the high heat stress. But when stressors with smaller influences are combined, no interaction takes place, right? And we observed this with studies that's combined both mild heat stress with hypoxia. So if this interaction occurs, it infers that there might be a maximum threshold for deterioration. So performance can only be influenced or decreased by a specific magnitude before the effects of one stressor are reduced or antagonized. And this seemed like a really possible mechanism for all the studies except for really my own. So another proposed mechanism could be that we respond to multi-stressor environments based on the task that we are completing. So again, all of the studies that observed that interaction use that time to exhaustion based protocol, whereas most of the studies that used a distance-based or duration-based time trial did not observe that interaction. So time trials and time to exhaustions can be difficult to compare because they have large differences in the motivation of each type of task. During a time to exhaustion, you work at a fixed intensity that cannot be adjusted during the task, and you're asked to just go for as long as you possibly can. So you only really have one behavioral decision. You either continue exercising or completing the task, or you stop. Alternatively, a time trial is different in that it has a fixed endpoint, and you have the ability to voluntarily adjust the intensity of exercise, typically in order to maintain a certain perception of effort, right? So you're either going for a specific distance or a specific amount of time. In other words, participants that complete a time trial can select a high yet conservative pace in order to maximize performance outcomes, but also ensure the likelihood of actually reaching that endpoint. So based on these differences, it's possible that the way sensory information is integrated into our perception of effort and fatigue could vary. Consequently, during a time trial, which involves pacing, you might be able to, you might integrate the effects of both stressors equally, while during a time to exhaustion, you might be able to downregulate or antagonize the effects of one stressor because you don't really have the option to pace yourself. So in conclusion, there's still no consensus on the exact effects of multi-stressor environments on physical performance or work capacity. But on a positive note, we do know that the decline in physical performance is not exacerbated or amplified, right? We're not getting an interaction where performance is hindered to a greater extent than the sum of the individual effects, which is a positive. And while this might be important for occupations where it's common for them to be exposed to a wide array of environmental conditions, such as military personnel or emergency responders. But this could even apply to an everyday general laborer who maybe is working or has moved to a different location for a job. They might find themselves in a different environment and experience decreased work capacity before an acclimation can occur. So a greater understanding of the conditions that lead to decreased physical work capacity can be important for identifying safe and optimal limits in these environments, but they can also aid us in developing training or acclimation protocols to produce greater and more rapid adaptations when we're exposed to these multi-stressor environments. And that's all I have. So I guess we'll get to questions.
Awesome. Thank you, Stephanie. That was a great presentation. We'll give a few minutes for people to enter any questions that they may have in the chat box. For now, looks like we have a few already. So first question, have you considered effects of altitude in underground, for example, in the mining environment? So the effects of depth or, yeah.
Yes, so as far as I'm aware, it hasn't really been looked into, but I know that when you go underground, you're not really experiencing altitude, as in you may experience an increase in barometric pressure, much like when you go underwater.
Mm-hmm.
But yeah, I'm not really sure if this would affect to or apply to an underground environment, because you don't really see that a rapid decrease in oxygen like you would at ascent to altitude.
One other question, would you be able to bring your conclusions that you have to local workers in the Sudbury area?
Yeah, I mean, in a way, it's a little different because we're not at altitude. But if someone from the Sudbury area were to all of a sudden find themselves either moving to a location where there is altitude, or in maybe a facility that needs to regulate oxygen quantity in the air for some reason, they are likely going to see a decrease in their ability to complete the task they're given for a period of time, because their body's not used to that decrease in oxygen availability. So maybe their ability to do, let's say they have to, they work on a conveyor belt, or in a more factory setting, maybe they're producing less of a product because they can't work as efficiently. But
Awesome.
hopefully that helped.
Are there any studies that have looked at multi-stressors on brain signaling pathways on how to establish the worst stressor takes precedence neural network? That's a toughie.
No, not that I'm aware of. It would definitely be the next step would be to, if this principle does exist, we need to definitely identify where in our physiological systems is that antagonistic interaction occurring. Clearly, it's not happening at the cardiovascular level. And there's some research that indicates that it's not happening at the peripheral, or the peripheral level. Like, there's no changes in the muscle's ability to produce force, but it hasn't been looked at in terms of a neurological or brain capacity.
So another question, what are the effects of air pollution with altitude? So the example given here is pollution worse in higher altitude, similar to is smoking worse?
Well, these are
Good ones, eh?
Yeah.
you can guess who asked them afterwards.
Honestly, I am not sure. I don't know if I have the capacity to answer that question. I will have to look into it. I'm sorry.
Yeah, fair enough. The questions are rolling in now. Has there been any research on performance under those varying conditions, so heat or altitude, where there are other rewards for prolonging performance, such as like safety or financial performance? Or rewards, sorry.
Not that I'm aware. It wasn't explicitly stated if there were rewards for performance, that, let's say, during the time to exhaustion trials. Mm-hmm. I would say typically in a research setting, not likely. I think in most of the studies, they said that participants were blinded to their performance results until they completed all of the conditions. So I think that tried to eliminate, oh, today I did worse, so it must have been, let's say, the combined condition. I mean, obviously you can't blind them to the physiological or the environmental stresses completely. When you're in a hot environment versus a cold environment. But in terms of the altitude stress, I think a lot of it was blinded. And I don't think there were other rewards for prolonging performance.
Okay. So I'll do two more questions here, and then we'll end it. And then if there are other questions, you can always email the CROSH account or try to find Stephanie directly. You can reach her through me. So second last one here. In the studies you looked at, was the baseline altitude that participants were exposed to taken into account with respect to how hypoxia affected them and the results obtained?
Yeah, so I'm pretty sure all of the locations in which these research studies were taking place were in locations that were very close to sea level. So it's unlikely that these people who participated in these studies were exposed to altitude in order to cause acclimation. So yeah, the control was always done at pretty close to sea level, so they should have the level of hypoxia should have been similar between studies, but I mean there was a large variation between the level of altitude they simulated.
And last one, do you think fitness modulates this additive interaction or relationship?
Yes, that's something we've also considered. Fitness level does, I think, play a part. Particularly in my study, we used trained cyclists, whereas in a lot of the other studies, they were just using recreationally active participants. And I think a lot of that plays a part in your ability to pace, which again could affect performance outcomes. So I think there is a huge disparity in that aspect, and it definitely needs to be looked into if fitness level plays a large part in this response. I feel like there's so many questions that have come out of this, and there's just not the research that coming out as quickly enough as the questions we can ask.
Right. Okay, thank you so much for all the questions. That was great discussion to have at the end. Stephanie, thank you again for your presentation. Super informative. Again, if you want to reach out to Stephanie for more information, please do so. I want to remind everyone that our webinars are recorded and will be posted on our website, most likely tomorrow. And we will give more information on our next webinar coming out next week, which will be at the end of May. So again, thank you everyone, and stay safe, stay healthy out there.